Okay, this is the review for cumulative number 3. And this is a test about higher degree polynomials. That was the first one of the two tests. And then rational functions. So I thought for today we would start with the higher degree polynomials. That's the stuff that you haven't seen for a long time now, especially since you're going to be watching this after the winter break there. This is going to be probably 3 weeks old, maybe 4 weeks old material. So what did we learn way back then? Well, get out your pencil or your virtual pencil and see if you can figure this out with me. So let's say we had negative 3x squared plus 2x plus 7. First few things where there was some terminology. The lead coefficient, you remember that? This thing is the lead coefficient. The lead term is this whole thing. And the degree, this is the degree, the highest power that you see. And they tell me all kinds of things. Like, for instance, I know that this graph would look kind of like this. It's negative in front, so it's going down at the end. That tells me the end value. The fact this is even tells me that it's the same as that end. That means it must be going down on this side. So now, if I take the y-intercept, which is where x is 0 and cancels off this and this, I would have y as 7. If I was going to have it go through 7 here, all I need to do to kind of give it a sketch would be find the y-intercept and then know how it begins and how it ends. So that's how we started off this unit for polynomials. But then it got much more complicated. By the end, we were doing this stuff. Do you remember the whole 2, and then there's a 1, 0, 5, 3, and then do the drop it like it's hot. 1 times 2 is 2, 0 plus 2 is 2, 2 plus 2 is 4. I'm going to make that negative 5. And then negative 5 plus the 4 would make negative 1. Negative 1 times 2 is negative 2. Oh, so close. I'm going to cheat a little bit and change that to a positive 2. Cool, there, it worked. So there's an example of synthetic. So we need to get you through factoring today. So today we're just going to focus on that polynomials unit and the key things that you learned there. All right, so back to day 1 of it was kind of like this. Let's practice that. I'd like you to try one. So I'm going to have a pause here in a moment where I want you to give this a shot. So let's say I had y equals negative 2 x to the 7th plus 3x to the 5th plus x plus 3. I'd like you to sketch mostly just how that begins and how it ends. I'll pause for a second while you give that a try. So I hope you looked at this and said it's going down on the right. I hope you looked at this and said, oh, the degree is 7, and that's an odd number. And then odd means that they're going to be different on the ends. So that means this end must be going up. Then I hope you thought, maybe I should just check what the y-intercept should be. The y-intercept should be, there should be a 3 there. And I put a, let's say that's 3. And then as long as I go through that spot, and I'm going up on the left and down on the right, you did it right. Okay. Now, we got more advanced about what's happening in the middle here when we started to write them like this. Remember what that would look like? To start with, I'll do one for you. If I know that this hits at negative 3, and, ooh, that's a special way of hitting at negative 3. If it hits right there, I know it has a root right there. And it's bouncing because it's a degree 2. We call that a double root. This doesn't have any power, so I'm going to put a 1 right there. And that means that at 1, that's another spot that it hits. Now, the same thing we knew before, the lead term, y equals x to the, let's see, this is x squared and another x to the 1 makes, and there's no numbers in front, so I can just put 1s. That makes 1x to the 3rd is my lead term. I know from the same method we just used a second ago that it's positive, so it's going up on the right. This number is positive. That's an odd number, and therefore it's different on this end. And I also have to be bouncing at this spot. Because of that, it's called the multiplicity. So if it's going to bounce right there, then let's see if I can make this work. This has to cut through. This has to bounce. And there. I'm heading down, and that looks like a good possible sketch. Now, I don't know exactly what the stretch factor is, to know whether or not I hit at the right spot here. But I could do it quick because the y-intercept is where? Hopefully somebody said x equals 0. If you put in a 0 here and a 0 here, we'd have 3 squared, which is 9. And then you'd multiply by -1 makes it -9. So that spot is apparently -9. So maybe I should have made it go down a little bit lower to make it look more realistic on the graph. But I can have this be counting by anything I want. So there we go. It's counting by 3s, and that'll be -9. All right, so there's an example of one. Let's see if you can sketch one of these. Imagine the cumulative test has something like this on it. And I threw in a negative in front. Pay attention. That's so easy to mess that up. All right, I'm going to pause for a second while you sketch a graph for me of that one. Okay, let's see how you did on this one. So hopefully you noticed that that was going down on the right. So easy to forget that. I'm going to start with that. And a lot of people might have started with the roots. So there's a root at here, -4. Because why? Because that makes it equal 0. Okay, so that's -4 is one of the roots, or the zeros. So that means it must bounce off of here. I said bounce because of that. That's a double root right there. Next, this one must touch 1, +1, just right there. And it does not bounce there. It does a cut through right there. All right, so if I make it go like this, and then bounce here, does that match up with my n values that I'd expect? Well, let's check it all out now. That's supposed to be down on the right. Good, it's down on the right. My lead coefficient here would be -x⁻³. That was taking this and this and that. That makes -x⁻³. And that negative told me to go down on the right. This 3 is telling me that these should be going opposite directions now. So the other end is going up. That's good. So now, I guess I could check my y-intercept. My y-intercept is where x equals 0. So I could put in a 0 right here. And I'd see if I had 4 squared is 16. Make it -16 because of that. -16 times -1 makes it +16. And again, depending on what scale I had, that could be a 16 right there. No reason it couldn't be. Or I could have stretched it up more. Either way. So there we go. There's a possible graph of that. What if they go the other way? What if they give you a graph and say, all right, here's a graph. And do you remember this kind? And then a bounce. And then let's make it cut through over here. Let's say they gave you that. Would you remember all 3 kinds? This is a single root. That's a double root. That's a triple root. Does it look vaguely a little bit familiar like that guy? The x⁻³ function. That's why it's a triple root. And that has a multiplicity of 3. If I was going to write the equation for this, I would write 1 parenthesis for that spot. Let's say it's touching here at -8. So then this would be x+8. Looks like it's just cutting through. It's not bouncing there. So I'm going to put it to the 1. And I'm going to have, oh, it looks like it's hitting at 0 here. Let's assume that that's 0. It's hitting at 0. I could say x plus 0. That counts. Or I could just say x, because x plus 0 and x are the same thing. But this is a triple root. Because of the way this thing is snaking through here, that's a triple. So that's to the 3rd. And then this part, let's say the other one's 8, maybe this one's 10, a +10. So then this would be x minus 10. And it looks like it's bouncing there. So I'm going to put a squared there. Now, Did you check? Did you look and see if it was going down on the right and therefore needs a negative in front? It is not going down on the right, but did you check? It's so easy to forget that. All right, so there's my equation. And if I was asked what's the degree of this polynomial, I would need to be able to find that lead term. I hope you can do that. X to the 1, x to the third, and x squared is going to make, they're all 1s on the front. 1, 1, 1. So this will be 1x to the 3, 4, 5, 6 to the 6th. That would be your lead term. And that's also telling me the degree. It tells me since this number is positive that it's going up on the right. And since this is even, that it must be also up on the left. So all of that worked out. Okay, so next I want to give you one of those. Let's see if you can handle it when there's, ooh, how about a double bounce? And then a triple. Okay, give me the equation. That's 8, and that's hitting at 3, and this is hitting at -3, and it's going down on the left and up on the right. Write an equation for that one. I'll pause for a second while you give that a try. Okay, so did you have y equals, I'm going to make a parenthesis for each of those roots. And we'll say this one right here is at x plus 3. It's a bounce, so we square it. This one's at x minus 3 because positive 3 needs to go in it and make it equal 0. And it looked like it was bouncing there. So I'm saying squared. And this will be x minus 8. And, ooh, that one looks like a snake. It's snaking through. So that's to the third power. Then, if asked, would you be able to tell whether, well, first of all, did it go down on the right? Did you check for that? It's going up on the right, so it should be positive in front. What's the lead coefficient and the lead term? X to the 2, 4, 3, 5, 7. X to the 7th. There, it's degree 7 or more. Don't forget that we could have imaginaries. All right, and that brings up a good point. Let's say you got something factored down and you got it to this. X squared plus 4, and then x squared minus 9. You've heard me say before, if you can factor it, you should. Even if it's equal to 0, should you still factor it? Yes, even more so. So I'm going to say x squared plus 4 and x plus 3 and x minus 3 because that's what this factors into. This was also the chapter where we introduced you to solving part of the zeros, finding the real roots and the imaginary roots. So this one right here would have root x equals -3. This one right here would have root x equals +3. And this has a little more complicated roots. Remember, we're trying to find what makes these equal 0. So x squared plus 4 equals 0. And then we solve it. X squared equals -4. Then I square root both sides. Then I get absolute value of x. Square root of -4 is 2i. Do you remember that? This is really like root 4 and root -1. And that's 2i. Okay? And then remember the absolute value is a reminder that you're going to have a positive and a -2i. That has 2 imaginary roots. There's 2 real roots, making a total of 4 roots. And should this have had 4 roots? Yes. If you want to see what it would have looked like ahead of time, it would have been an x to the 4th plus, I'm just going to multiply it out, negative 9x squared and positive 4x squared makes negative 5x squared. And then the last would have been 9 times 4, negative 36. It could have started like that, then got factored into this and this, and then got factored further. And then you got to know you can't factor that because it has a plus in there. But you can still find the roots. All right. So imagine you had one like this, x squared minus 3, and then x squared plus 2, and then x plus 7 equals 0. There's quite a few ways to make this equal 0. That's going to have 1 root. That's going to have 2 roots. That's going to have 2 roots. Total of 5 roots. Why? Because the lead coefficient, lead term, would be x to the 5th. So there's 5 answers for this thing. What are the solutions? What are the real ones? What are the imaginary? Give it a try. I'll pause for a second while you do. Okay, solve this one. First of all, I'm just going to move these guys over a little bit. I am going to take each of these and simply set them equal to 0. X squared minus 3 equals 0, and I'll solve. And I'll take this one and say x plus 2 has got to equal 0. Well, that's pretty easy. X equals negative 2. And then I'll do this last one. Let's just put x equals negative 2 onto the real answer just right away. Now, this, I don't know if it's real or imaginary yet. I'm going to do a little more work first. First, I'm going to add 3 to both sides, so I'll have x squared equals 3. Now, when I square root, if I'm square rooting and getting a negative, then I'm getting an imaginary. That is a square root, but that is not imaginary. Absolute value of x, square root of 3. That brings in a plus and minus. The square root of 3. No negative under the root, so that's real. You put it right here with the other. Plus and minus root 3. Those are real roots. 2 of them there, 1 of them there makes 3 reals. Now we got to find the imaginaries. That's this one. X squared. Uh-oh. I just caught it. I'm sure you guys caught it before me. I screwed up and I solved this one like it was just a regular x. I'm sorry. I'm going to have to fix that. This is not negative 2 right here. Ha! You're all laughing at me, but I'm laughing at you because I'm in Hawaii. Okay, anyway, so back to if I have x squared plus 2, and I need to solve that one, I set it equal to 0. X squared equals negative 2. And then I'm going to square root. I'm going to absolute value of x. And I'm going to get plus and minus. And then that negative underneath the square root needs to come out. Remember how you make an I for that? And then square root of 2. All right, so that is the imaginary roots. Okay, so those were imaginaries. So I'm going to put those over on the imaginary line here. Plus and minus I root 2. Don't just assume you can do these in your head, because a lot of people will say that that's plus and minus 2i. It's a really easy mistake to make. All right, now I'm going to solve that x plus 7 at the end there. X plus 7 equals 0, so x is equal to negative 7. So that's the other real one, is negative 7. So there's 3 reals and 2 imaginaries, total of 5. That makes sense because this was a degree 5 polynomial. Okay. Remember, that's all about setting these equal to 0. All right. So, what else was in that chapter? That was the one where you had to factor big, huge, scary things. But let's not start with huge, scary. Let's start with x to the third plus 3x squared minus 2x minus 6. Do you remember factor by grouping? If you do, would you please try that one with factor by grouping? Okay, and here's what you should have had. Should have noticed that x squared comes out of it, and you have x plus 3 left. And on this part right here, negative 2 comes out of it, and you have x plus 3 left. And if that and that are the same, then they can be factored out to the front. X plus 3, and then what do I have left? X squared minus 2. I'm hoping that's just like second nature to you now. You practice that a lot. So that's an example of one that's now been factored. What if it was equal to 0? Well, then you could set each of these parts equal to 0 and solve them. I get 2. Can you tell that those would be real roots? Because when I set it equal to 0 and add 2 to both sides, you'd have x squared equals 2. There'd be no negative underneath the square root. And this would also be real. So there's a total of 3 real roots, which makes sense considering the original polynomial was to the third. All right. So that's one kind of factoring. Then there was another kind of factoring. Let's say I gave you this big, scary polynomial, x to the third plus 7x squared plus 13x plus 6, and I said that negative 2 was a root. Now, I'm not even going to review long division because I don't think we're going to have to like what we were going to make you do will require long division. I will just show you how you'd set it up. If you were going to do long division, it'd go like this, and you'd say what number goes here, and you go, okay, well, I guess I'd need an x squared there. So this times this makes this, and this times that makes 2x squared. And you draw a line opposite opposite. Remember that? Well, I think we can get away with just using not long division, but synthetic division. All right, so if they tell you -2 is a root of it, then you can put -2 in the little box as opposed to what this was a factor. It's important you get the difference. That's a factor. That's a root. The root is the thing that makes it equal to 0. That's why we call it a 0 also. And then I'm going to put in a 1. 7, 13, 6. Draw a line. Quick note, there's degree 3, degree 2, degree 1, and then the plane constant, which would be, you could think of as a x to the 0 term. There was no missing terms. If there was, you'd need to hold a place with a 0 like that? All right, just a quick reminder to watch out for missing terms. Okay, now let's practice this. This drops down. 1 drops down, drop like a tot. 1 times -2 is -2. Add them, multiply them. 2 times -5, -10. Add them. Let's see, 13 and -10, that'll be a 3. 3 times -2 makes -6. And I know it worked because I got a 0 at the end. That's the remainder. Do you remember how to interpret this? Let's say this comes down and becomes x plus 2. And then this part right here is, these are the x to the 0s, x to the 1s, and x squared. So it's x squared plus 5x plus 3. Now you know my saying, if you can't factor it, you should. But that can't be factored. So if that can't be factored, then we can't factor it anymore, and it's all the way factored already. I don't want that to freak you out. If you wanted to know what made this equal to 0, well, there's two things. You can make that equal 0 easily by putting in a -2. So -2 is one of the zeros. And if you can factor it, you should, but if you can't factor it, you could always use the, I hope somebody said quadratic formula. All right, so that's just a quick reminder of how that synthetic works. Now, I'm going to give you one that I know you could solve it with factor by grouping, but I'm suggesting that you not. I'm suggesting you practice this. X to the 3rd plus 5x squared minus 10. No, let's make it 2x and then minus 10. That one can be factored by grouping, but don't. Instead, and no, don't use long division either, use synthetic. And I'll tell you that -5 is a root of this thing. And then let's see if you can factor it all the way. I'm going to pause for a moment while you factor this puppy. Okay, here's what you should have done. You start by bringing down these numbers, the coefficients, 1, 5, -2, -10. Draw a line. 1, -5, -5, add them, multiply them, 0, add them, -2, multiply them, +10. Sweet, canceled. That's what it's supposed to do. And now I factored it, and this becomes x plus 5, no difference, root factor. This thing, I would say this is x to the 0s, this is x to the 1s, and this is x to the 2s. Better clean that up. This becomes x plus 5. And this becomes x squared. I don't need to write plus 0x minus 2. Now, I want you to just think for a moment. You factored it, right? Did anybody ask you to find the roots? No. But what if they said, does this thing have imaginary roots? Would this have imaginary roots? Well, you would have really needed to factor it. That's why we keep coming back to, if you can factor it, you should. Because now that it's factored, you can figure out the roots. That's x equals -5. That's not imaginary. And this, x squared minus 2 equals 0. When I go x squared equals 2, notice that's a +2. When I square root, am I square rooting a negative? No. This one does not have imaginary roots. If it just asks you what are the roots, then you'd have to finish it. Absolute value of x is square root of 2, and that brings in the 2 plus and minus square root of 2. There we go. And this is also real. That may seem weird, but it's not imaginary because there's no negative underneath the root. So that has 3 real roots. So if the question was, does this have imaginary roots? You don't know until you factor it. Once you get it factored, you set it equal to 0, and then you solve stuff. And if there's one that has a negative underneath the root, then yeah, it'll have imaginaries. By the way, if it has any imaginaries, they'll be in sets of 2. Always a plus and a minus of it. Okay. So I think that pretty much covers the polynomials unit. And I hope that you have a worksheet that you can work on for tonight, the review worksheet for the polynomials test. And you should do that part of the worksheet that has to do with the polynomials part of the test. All right. Have a great day.